covering 9-2 today, which is piecewise functions. So we're going to graph and evaluate piecewise functions and write piecewise functions. So before we do that, we're going to need to figure out what a piecewise function is. And so here's our definition. Piecewise function is a function that's a combination of one or more functions. So normally you have multiple equations within a piecewise function, and each equation is defined over a set domain, and that means a set number of x values. And within the definition of the piecewise function, it tells you what part of the x-axis that a particular piece is valid. So the rules for a piecewise function is different for different parts of the pieces of the domain, and that's just basically what I said. And before we start writing and looking at piecewise function definitions, I want to remind you that when we're talking about intervals, the square bracket means an endpoint is included. Parentheses means that it's excluded. And we're going to need to know that for our piecewise functions. So let's start looking at piecewise function. This graph is actually an example of a piecewise function. So it's about an important topic called namely mixed nuts. We all need to know about those. And it's a graph that graphs weight against price per pound of mixed nuts. So what's this telling us? It tells us, notice these open circles here, and then we have the closed circle here. So that means that this point is not included here, but included as a part of this. So basically between 0 and 2 pounds, the cost is going to be between. All right, so it says that between 0 and 2 pounds, we have a cost of between 0 less than 2 pounds, we have a cost of 8. So it's not quite 2 pounds, 2 is not included. But between 2 and this point, which is 5, so less than 5 pounds, it's going to be a cost of $6. And from 5 pounds on, the cost is going to be $5. So here would be the table that you would create, 0 to 1.99, and you could put 99999 if you wanted to, but this is good enough. 0 to 1.99 pounds, $8. 2 to 4.99 pounds at $6, and 5 or more is $5. So notice how the open circles are taken into account by these values here. And also notice, if you remember about functions, you're not allowed to have two y values for the same value of x. So I'm not able to, here we go. So you can see how with this open circle here and here, even though the lines actually are on the same x value, only one of them has a value that is valid for x equals 2 or x equals 5. So that allows it to be called a function for that reason. All right, this is one for you to try, and you probably already see the answers, but it'd be a good idea if you try it without looking at the answers so that you understand a little bit about piecewise functions coming from this direction. All right, so a piecewise function that is constant for each interval. In other words, the equation is just going to be y equals k, where k is some number. And it says such as a ticket price. This is an example in the book. It's called a step function. So instead of having equations for each piece, you have just basically y is going to be a constant. And the example we just looked at with the mixed nuts, that is a constant. That would be a step function because, let's go back and look at that. The value at each particular piece of the function is the same. It's a constant. So this would be a step function. Whoops, one too far. All right, so this is what the equation would look like. I think for our mixed nuts example, it would look, actually let's try and do that one. Well, actually, let's talk about this first. So this says this is the function equation, and it's just a little more complicated than what we're used to. This says the equation for the function f of x the value of y, or f of x, is equal to 5 when x is between 0, greater than 0, and less than 13. So that means if we had a graph here, this is 0 and this is 13, you would have y equal to, have open circles, 5. This says the value of the function then is equal to 9 when it's greater than or equal to 13. So notice this equal sign, and that means we are going to, where's 9? Let's see, we'll just make 9 here. We're going to have a closed circle here at 13, and then to 55, notice it's less than 55. So 55 over here, it's going to be an open circle, and it's going to look like that. And then finally, it's going to be, no, that's not going to work. It's going to be 6.5 if x is greater than or equal to 55. So how would that look? When x is 55, it's going to be 6.5 here. You can't see that, can you? Let me change the color of that. It's going to be 6.5, which is somewhere in here. You're going to have a closed circle because it includes the point 55 because of the equals, and then just a straight line with an arrow. So you can see how each of these lines is basically like a separate function, and the function only exists between the ranges defined here. So these are the if defines your conditions for when that function is valid. Outside of these ranges, the function doesn't exist. So you can see, and this makes it so it is a function because we only have one value of this whole function, f of x, at any given, for any given value of x. All right, so evaluate each piecewise function for, and this says when x is equal to 1 and x is equal to 4. Well, that's really quite ugly. So here's our piecewise function, and we need to figure out which of these equations we want to use. And we're going to figure it out based on the value of x they give us. So the first one says x is equal to 1, or negative 1, sorry. Which of these is valid when x is equal to negative 1? Well, this is for x less than or equal to 2, and this is for x greater than 2. Obviously, x equal negative 1 is going to be in this range, or actually this domain. So we're going to use this equation. So f at negative 1 is going to be equal to 2 times negative 1 plus 1, which is going to be negative 1. Next one, when x is equal to 4, obviously x greater than 2 is when x is 4, it's going to be greater than 2, so that means we're going to use this equation. So we're going to plug x into that equation instead, and we're going to get 12. So piecewise functions, evaluating for a particular value of x is a little bit more complicated because you're going to have multiple equations you need to figure out which one to use. All right, here is one for you to try. And answers are there. Hopefully you figured it out before you looked at the answers. All right, now we're going to look at graphing. How do we graph a piecewise function? Well, it's like graphing two separate equations. So here's our function, g of x equals 1/4 x plus 3 if x is less than 0, else it's equal to negative 2x plus 3 if x is greater than or equal to 0. So first of all, we see that basically we're going to cut our graph, our axes, xy axes, in half. And it's going to be cut in half based on x equals 0, which happens to be our y-axis. So this is x equals 0, which is our y-axis. When x is less than 0, this graph is going to be graphed. When x is greater than or equal to 0, which is that part of the grid, we're going to use this equation. And it's pretty much that simple. So for the first branch, the function is 3. So now we've broken it into where we're going to put our graphs. Now we're just going to create the graphs themselves. This is a linear function. It has a y-intercept of 3. But notice it's less than 0, so this is going to be an open circle. Actually, let me use a different color so you can. So this is the open circle, and then we have a slope of 1/4. So we're kind of going to have to work backwards. Means we're going to go down 1 and over 4. 1, 2, 3, 4. So this is our point. So we have an open circle, and then it's going to go in this direction forever. So you should have an arrow. So it's the same linear function we would graph, except it stops at the y-axis because it doesn't exist when x is greater than or equal to 0. This one starts when x is greater than or equal to 0. Notice again, this one has a y-intercept of 3, but since it's equal, we're going to make this one have the closed dot. And then it has a slope of -2, so we're going to go down 2 over 1. Draw our line, and again, it's going to go forever in the x greater than 0 domain. And that's going to be your graph for your piecewise function. Okay, next example. This time we have 3 different functions, and we need to know where on the graph to graph these. So this piece of the graph exists when x is less than 0, so in the negative part of the x domain. The next piece of the graph exists between 0 and less than 4, and then this piece of the graph is greater than or equal to 4. So if you think about it, we have broken our graph into 3 pieces. This is piece 1. Piece 2 goes from 0 to 4. So if this is 4, and then piece 3, so this is 2, and then this is 3. Whoops. This is going to be 2, and this is 3. So this is my graph 1, this is my graph 2, and this is my graph 3. So once we've defined what part of the grid they belong in, now we can just start graphing them. Notice this is a quadratic, so we need to graph the quadratic starting from 0. So when x is 0, and you can do this however you want, I would probably draw a table, make a table. They actually make a table for all of them, and you can do it this way. I mean, they have all their function definitions up here. And what they've done here is only evaluate the function that's valid. So this is going to be less than 0. So when x is equal to -2, this is going to be -2 squared 4 minus 3 is 1. This is going to be 1 squared minus 3 or -2, and when x is 0, it's -3. So notice it's less than 0, so it doesn't actually have, this is going to be an open circle at this point. We know quadratics are parabolas, so what we're going to do is we're going to make our open circle, whoops, sorry. We're going to make our open circle here for that. And then we have a -1, -2, and then a -2, 1, which is here. So this is our parabola. It goes forever in that direction. Next one, it's a linear function. It has a y-intercept of -3. So again, they share this point, but this one actually is going to be the solid dot. And then you have a slope of 1/2. So if I go up 1 over 2, and I'm going to draw my line until I hit 4. And notice this is does not have an equal, so you could make an open circle here. And then our last part, again, this is quadratic. So we don't want to start evaluating it until it's valid. So we're going to start, our first point we're going to start evaluating is when x is equal to 4, which is here. When this is 4, it's going to be 0 minus 1, so it's going to be 4 -1, which is, again, Notice how these points, and it doesn't always happen like this where these points actually are at the same spot, but in this case it is. So this one would be a closed circle, and then they did 5 and 6, so we have 0 and then 3, and that's our function. It looks funny, but that would be the graph of a piecewise function. Oops. I think there's actually one more thing to say down here. It says no circle is required. Basically, they're saying no circle is required here or here, since we have two things that are joined. So you can't really tell. If you're doing it in pencil, you couldn't really tell which one was the closed or open circle. It just might be good to get in the habit of it, because if for some reason, instead of starting here at -3, this one started at had a point at 0, -1, then you would make sure that you would want to make sure this was closed and then this one were open. So it's just a good idea to get in the habit of making closed and open circles with the functions. Okay, here's one for you to graph. Make sure you understand how to graph the different pieces. Whoops, yeah, that's right. All right, now we're going to go to the more complicated part. Is we're going to have a graph and we're going to have to write the function. So remember, it's broken into pieces, and you can kind of see where the function changes, and those are the first things you want to identify. So you can see we have a change here and a change here, and this is for the value, and I know this isn't a very good big graph, but this is 0, 0.5, 0.5. So you're looking for the value of x at that point. And this one, here's a transition, and this is 1.5. This is actually backwards. This is actually 1.5, 12.5. So the values of x where the transitions, where the function definitions will change, are going to be 0.5 and 1.5. All right, so now, knowing that, it doesn't matter. We don't know which one owns, basically which one would be the open or which one would be the closed circle. So you can choose which one has the equal sign on your inequality. I think most of the time, well, I'm not sure. I remember the book is consistent. It chooses either the first part or the second part of the function to have the closed circle or open circle, and I don't remember which is which. I'm just going to say only one can have that point, so you can only include that point you can only include 0.05 for this piece or this piece, and it doesn't matter which, just not both. All right, so we're going to write the equations. These are all linear functions, so point slope form is this. It's easy to start in point slope form. It's easiest to start in point slope form, but it doesn't matter. You just need to figure out the linear equation. So we see here that our y-intercept is 0, and what is our slope? Well, it looks like our slope is going to be up. These each are 2. So it's going to be, well, here's our slope. We go from 0, 0 to 0.5 over 0.5, which is basically going to be 1. So if it were y and x, if our variables were y and x, it would be y is equal to our slope of 1 times x plus 0, which is y is equal to x. But they're using t to be our independent variable and d to be our dependent variable, so it's d is equal to t. All right, so this next piece, we don't know what our y-intercept is, which is why they suggest you use point slope form. We have this point here, and we're going to plug that in for our y1, x1. Our slope we can figure out by using these 2 points. So if we have, if this is, oops, I'm sorry, let me get some decent colors here. So if we have 0 0.5, 0 0.5, 1.5, 12.5, and we use the slope formula, we're going to have 12.5 minus 0 0.5 over 1.5 minus 0 0.5, which gives us a slope of 12 over 1, which is 12. So it's going to be, whoops, so the equation would be y minus, and whichever point you chose to use, it doesn't matter, 0 0.5 equals 12 times x minus 0 0.5. You're going to distribute and then add your 0.5 here, and that's going to get you to this final equation, which is what they did. So it's going to be d is equal, that is terrible color, I'm sorry, d is equal to 12t minus 5.5. And then our last piece, again, if we, here's the point, and again I think these are backwards, so I better fix this in the real one. It's going to be 2 and 15.5. So find our slope using these 2 points. It's going to be 15.5 minus 12.5 over 1.5. Whoops, wrong one. Over 2 minus 1.5 equals 3 over 0.5, which is going to give you a slope of 6. And then if we use the point 1.5 and 12.5 to plug in for y1 and x1, distribute and put in slope-intercept form, then this is going to be our final equation. So we have our equations. We're going to create our rule. D of t equals brace, squiggly brace, and then the first piece. So notice the d of t, you don't actually write this again. This is covered by this. So you're just going to write the right half of all these equations. So it's going to be t. When is it t? It's t between 0 and 0 0.5. And they did include 0 0.5 with this piece. Next equation, 12t minus 5.5. Where is that valid? Between 0 0.5. Notice this one cannot have the equal sign since I used it up here for 0 0.5. And 1.5. And then lastly, our third equation is valid between 1.5. Actually, it looks like it's valid based on that, what that looks like. It should be if t is greater than 1.5 because it has an arrow on it. And that would be your equation. So it's basically writing 3 different equations, and then you just have to add in your domains where each piece is valid. And it's a lot of work, I understand that. But every step is something that we've done multiple times, so hopefully it won't be too challenging. All right, so this would be one that I would want you to try. And it, just so you know, these are, whoops, these are the boundaries. They kind of show you or where there are transitions. So actually, I think there's only one transition, which is right here. This looks like it's all part of the same. So there's one transition at this value of x right here. And they just allow you to use the rest of the points to help you write the graph, the functions for the graphs. All right, so that is piecewise functions. If you have questions, please bring them to class. Otherwise, here's the homework, and there is going to be a new web activity up.